Okay, so for our next speaker, we have John Shortt, a PhD student at the University of Ottawa. John, please take it away.
Thank you. So what I'm going to talk about is essentially, we're going to say the execution cost of a WebAssembly function is the number of instructions an interpreter would execute when running that function on its inputs. So clearly this is a woefully inadequate definition of execution cost, but let's go with it and see where it takes us. I'm going to talk about the motivation for this work, some of the work that I did earlier for my master's thesis, the approach to the work that I'm doing now, and what's next. So the motivation effectively is that WebAssembly runs in a sandbox, and what's run is arbitrary code. So shouldn't the host be able to know what the cost of running that code will be and make a decision about whether or not to run that code or not, depending on the cost of running that code? Today, the method that's used primarily is to run the code and kill it when it's consumed the resources that the host would allow it to use. It's too late. In strong terms, the damage is done. So if we knew beforehand what it was going to cost, then we could mitigate that damage. So for my master's thesis, I kind of outlined an approach to bounding the cost of a single WebAssembly function, not the entire call tree, just that single function. And the things that I used were things from compiler technology, theory of programming languages in general, including basic blocks, flow control graphs, and iterating over flow control graphs, symbolic execution, slicing to find loop constraints, and understanding the parametrization of loops. I also implemented all of this in OCaml, a utility called wanalyze, which was about 5,000 lines of OCaml, that included a binary parser for WebAssembly modules, which I kind of recommend as a project to anyone who wants to have a deeper understanding of WebAssembly. A symbolic execution engine, because in order to understand the performance of loops, I needed to understand symbolically how the constraints in a loop were being constructed and operated on, and all the other concepts from the previous slides. In the end, I was able to produce numeric bounds for non-looping functions, which is kind of a straightforward thing to do, and symbolic bounds for some looping functions, assuming that we could solve the loop constraints, assuming that we had a solver that could solve the looping constraints, and there's a lot of literature about that, but assuming that we could do that. And one notable thing that happened here, I tested this on a small but large, small number of programs, large programs, medium to large size WebAssembly modules, including everything from a Bitcoin miner to Doom and AutoCAD, and combinatorial explosion of the paths, the possible paths within the body of a loop rarely actually occurred. I set an artificial limit of 1 million possible execution paths through a loop, and I would say in less than 5% of the loops that limit was achieved. So this was kind of encouraging. Okay. So when I finished that project, what remained to be done? When essentially defended my master's. So one of the issues, what I did was, there were a lot of results that I stated as facts with arguments, but not what I would consider to be a proof. And so I wasn't happy with the sort of rigor of what I had done. I needed to implement those loop solving techniques from the literature, and there's like 30 or 40 years of literature on this. I wanted to extend it to do the full call tree of a function and do more performance testing and performance measurement. So now I'm focused on the first point on this slide. And so I actually was aware of the work that Conrad had done in mechanizing the proof of preservation in progress. And I picked up the GitHub project for that last year and looked at it, and I kind of realized that there was also something very interesting in this, which was a generated from the Coq implementation of a WebAssembly interpreter. So this is interesting. How can I use this to further my goal of making my own work more rigorous? So it's kind of clear at this point what to do. I need to formalize in Coq all the things that are needed to implement the bounds checks that I implemented in my OCaml code in Coq, leveraging the definitions, the Coq definitions that are in wasm-cert today, and by the way, making sure that I don't break the things that wasm-cert proves. And you know, after playing around with it a little bit, it became kind of like essentially building and running the project. It became clear to me that this was, you know, not hard to do. I could break the proofs that were in there by doing stupid things. So as long as my reasoning is as long as I haven't done anything stupid and the proofs still work, then everything that I've done should be fine. And then furthermore, I could extract to OCaml a program that does what the OCaml code that I have today does, but with one significant benefit. So I dug into it, and here's just a snippet of code in Coq with the things highlighted in green that I reuse from the wasm-cert project. So basic instruction is the long inductive definition in Coq that defines all of the instructions in Coq. So essentially, my definition of basic block is a list of instructions in WebAssembly that contain no control flow, no instructions that can cause a change in, or be the destination of a change in flow control, with no such similar instruction in the body. This is a simple and obvious way to define basic blocks. And then I defined two functions, is basic block and basic blocks of expression. So that's essentially taking the body of a WebAssembly function and producing the list of basic blocks that constitute that function body. And then I have to prove a lemma that my definition that these definitions are consistent, that I'll correctly produce a thing that is a list of basic blocks from from the function that creates the list of basic blocks. So this is a flavor of the kind of thing that I have to do. You know, the other kind of thing that I have to do is that I'm studying flow control graphs, and I'm analyzing the costs of executing this is a flow control graph of basic blocks. I'm studying the cost of executing the cost of executing the basic blocks in this graph. And if for a moment we ignore the fact that there are loops in this control flow graph, we can we can see that from a graph like this that contains no loops, we can easily derive the cost of the function. To allow analysis of loops, essentially I aggregate the basic blocks that make up the loop into larger blocks that I call loop blocks, where a loop block contains all the consecutive basic blocks within a loop that don't that are inside the boundary of that loop. And this is an example of this is actually a diagram produced for a bubble sort function that contains a loop and a nested loop, and contains some preamble code. So I need to define this kind of structure in Coq and then write Coq code to do the analysis of this structure to discover what I need to know about loops. So what I need to know about loops actually comes from the fact that there's really only two graphs or two forms of graph that a loop structure in WebAssembly can have. And essentially it's, we check the condition of the loop, the guard of the loop, and branch to the top of the loop in a loop that continues effectively, or we branch out of the loop in the case of a loop that breaks. So I should say that to do this analysis, I've taken a loop and created a copy of that loop, a control flow diagram for a copy of that loop for every possible path through that loop. So this is where the combinatorial explosion can occur. But essentially, I have a very simple view of a loop. It's, it kind of looks like this, like one of these two things, and it is amenable to an analysis that's kind of simple when we look at it just in this form. And so the things that I need to parameterize the loop is the condition for the loop continuing, which is the condition on the branch if statement. I get that by symbolically executing a sliced version of this code. And it's sliced because I know the variables that are in the condition. Variables, I mean in a very general sense. It could be memory, it could be global variables, it could be local variables. I know what the initial values of this variable are when we enter the loop. And from the slicing, I also know how the variables are updated as the loop executes. So this essentially gives me, I think, everything I need to give to a solver to tell me how many times this loop will execute. The problem is that this is all symbolic, so that's going to be challenging. So why am I doing all of this when I have an OCaml project a program that already does it? And of course, the answer is to get some rigor in what I've done. And specifically, the benefit of the rigor will manifest in the fact that I want to be able to prove in Coq this family of inequalities. So what these inequalities, so you actually, obviously you read these inequalities from the bottom up, not from the top down. So these inequalities are sort of a set of recursive, nested inequalities that go from determining the cost of a basic block, which is simply the number of instructions in the basic block, through the cost of the path of a basic block, which is a path made up of basic blocks, which is essentially the sum of the costs of the basic blocks in this path, and then proceeding upwards to the cost of a loop, and then to the cost of a function. So and you'll see that there's the presence of this magic in 4.2 n of e and x, which is for a given loop denoted by e, and inputs x, how many times that loop iterates. So this is something I need to solve, but essentially, if I can prove all of this in Coq and generate an OCaml program that produces the cost on line 4.1, which is the cost of the function, then I've achieved in building a framework that allows this cost to be determined in a verified way. So once I've got all that done, what will be left to do? I'll need to implement other things that I talked about earlier, but I'll also be able to compare this to my existing OCaml implementation. So I'm kind of interested to see where that will fall from a performance point of view. And there are other issues when it comes time to the implementing the entire function call tree, obviously. And I should say that what I've done so far is strictly based on WASM 1.0, and obviously there's lots of work to do for WASM 2.0. So my conclusion is this. WASM has a minimal spec from the point of view of program analysis, because clearly we need to add many concepts in order to do interesting program analysis of WASM programs. I think that wasm-cert is a good starting point for this, and I think this project, as I work on it, will bear that out. And this gives us a path to verified program analysis for more than just the problem that I've described. This in a sense is a prototype or an example of a problem that can be solved with this approach, and I'm hopeful that I'll be able to use this as a proof point to espouse that approach. So as Conrad said, I'm a PhD student, third-year PhD student at the University of Ottawa. I'm working with Amy Felty and Anil Somayaji as my advisors. They've helped me with this work. And with that, I'd like to thank you for your attention and answer any questions you might have.
Thanks so much. That was a great talk and perfectly in time, so we have time for some questions.
I've got a couple of questions. So first, you were a bit disparaging about your cost analysis at the beginning in terms of saying, well, this is what I'm doing, and you didn't sort of justify it, and sort of now stepping back, and you're not an MSc student, you're a PhD student. What are you thinking about sort of better cost functions or properties?
Well, I mean, specifically, this is costing WebAssembly instructions, and so those get, in the use case that I'm thinking of, typically get compiled into native machine code, which may or may not have the same characteristics as the interpreted WebAssembly code. So that's one point. The second point is that clearly the cost of a memory load is significantly different than a cost of a a register move or a multiply instruction compared to an add instruction. So there's a granularity there that in a useful tool would need to be expressed, and I'm okay to ignore that because I think that's something that could be added in later. And when all of a sudden.
And also another question. So my student Rao and Conrad and I in Popple have got a paper where we have an interpreter, and the point is when you extract, all the proof gubbins doesn't cause any problems to do with performance, i.e. what you hope to get from the interpreter is what you get. And we had to work quite hard to get that done. And what do you think regarding your analysis, cost analysis? Is it entwined with the wasm-cert? So when you're extracting, are you going to lose performance compared with the one you did directly in OCaml, or are you going to?
I'd be stunned if I didn't lose performance.
Yeah.
Right. I mean,
yeah.
I don't know concretely today what that might be.
Yeah.
But I would expect.
Yes.
That I will. And the good thing about having the hand-coded OCaml implementation is that it gives me a concrete target that I'll work towards and understand. So yeah, I look forward to getting to that point.
Thank you.
Yeah, I guess as I meant, as is quite obvious, I think this is work in progress. This has just begun more than anything.
So I have one last question, but maybe while you're answering it, can we get Lucy up onto the stage to swap the laptops? So my just final question is, I liked your kind of point that you focused on this cost analysis, but that doesn't have to be the only thing you're thinking about when building this kind of verifying tool. What would be the second analysis you would be looking at if you had time to do one more?
Yeah. I think I'm drawn to things like taint flow and security-related issues. I made a note as the last speaker was talking that memory consumption could also be an interesting thing. If there's a loop that's allocating 2 gigabytes of memory per loop iteration, and I can tell you that that's what happens, that'd be pretty interesting. So those are kind of very direct. I think more generally, there will be other interesting program analysis tasks to undertake. I'm confident of that. Thank you.
Thanks very much. Let's thank John again for his talk.